Okay, welcome to autonomous driving. So just a reminder that the homework, the assignment is due tonight. Do people have difficulty with the assignment? So how many people cannot finish it tonight? Say something or send out a chat.
I submitted my assignment in the morning today.
Okay, that's good.
Did you receive it?
Let me check.
I submitted on Kinematic.
Yeah. Okay, now I have submission from a few people, 3, 4. So that's good. So I hope you can finish because I got a request to extend the deadline. But I think I shouldn't because the assignment is pretty simple. You can finish it in an hour. So yeah, let's keep the deadline. So I have another assignment out, which I'll discuss after discussing the lecture on control. I updated the slides to introduce more details on the bicycle model, which is useful for the second assignment. So yeah, please go ahead and download the latest slides, both L3 control and L4 planning. So here's the overall system autonomous driving framework. So last lecture we were discussing control. So here's a more detailed description of the vehicle control architecture. So the planning module actually consists of 2 parts: path planning, path generation, and speed profile generation. Specifically, that's a local planning step. Actually, yeah, there's mission planning and behavior planning are not shown here, so I should say that. Local planning step. And then the planner provides reference positions, that's a path, and reference velocity, speed along the path. So reference, and then the controller needs to follow the provided trajectory by performing longitudinal control, which follows the reference velocity, and lateral control, which helps to track the reference position. And longitudinal velocity V is shared among the lateral control and longitudinal control because the car is a so-called a bicycle model. It cannot move sideways directly. It has to turn and move forward. So that's why the longitudinal velocity is useful for both longitudinal control and a lateral control. And finally, the last step is actuation. The longitudinal control provides actuator inputs for throttle angle and brake position to control throttle and brake. And steering lateral control provides steering angle to control the steering. So the feedback control problem is to design a controller to let the system track a given reference signal. Could be a reference velocity profile, could be a reference heading direction. So we saw this video to describe the intuition behind PID control. So you have a P term where the control input is proportional to the error, and I term where the input is proportional to integral of the error up to time t, and derivative term where the input is proportional to the derivative. So I added the table to summarize the effects of the three parameters. Increasing Kp decreases rise time, increases overshoot, and decreases steady state error. That is, you're controlling harder, so you're pushing harder on the system. Increasing Ki decreases rise time, increases overshoot, similar to Kp, and increases settling time, and eliminates steady state error. So that's important. Kp, no matter how large it is, you cannot decrease the steady state error to 0 unless you have infinite Kp. But adding a Ki helps you to reduce it to 0. And Kd, increasing Kd helps to decrease overshoot and decrease settling time. Yeah, so that's the general effects of the three parameters for PID control. So we saw this vehicle lateral control problem where the reference trajectory is given as 0, 0. That is, you want to go travel straight ahead, center of the lane. And then you're controlling the turning angle. So the velocity is constant, speed is constant. So your desired state, the reference is going straight ahead in the at center of the road, and then you're controlling the theta parameter, not controlling the velocity, which is given as a constant. And then we have the linear system dynamics by linearizing based on small angle assumption. So we have the approximation of transforming the nonlinear function sine theta to a linear function theta. So the overall system dynamic is linear. And then when we have a linear system, we can perform controller design based on well-known methods in control theory. So in all my slides, my second level indentation is this symbol, which is, I find it to be annoying. Yeah, it's not a minus sign. And then we get the error signal. That's the difference between the reference desired system state and the actual system state, and then we plug in the controller as the P controller, no I or D terms, we get the closed loop aerodynamics. So the goal is to design the P parameters here. Because the state is a vector, we have two P parameters. One is for multiplying with the distance to center of the lane, d. One is for multiplying with the heading angle, theta. So we need to design the P parameters to drive the error to 0. So any questions on the up to this part? And then we perform pole placement and solve for the relationship between KD and K theta to have a so-called critically damped dynamics, which is essentially has overshoot of 0 and has a fast convergence to reference. And then we to maintain a small angle assumption, to maintain that theta as magnitude does not exceed the threshold, we impose a upper bound on the dt used for computing the P controller. So the normal P controller has kd times dt in this equation, but we instead we clamp it. We clamp it to a lower and upper thresholds to just to ensure that even though the vehicle is very far from center of the lane, even though dt may be large, we're not changing the heading angle very fast. So we try to change the heading angle in a smooth manner. And then this helps to ensure that the small angle assumption, theta t magnitude does not exceed theta threshold, is satisfied. But it's not a hard guarantee. It's a kind of a heuristic to help ensure the small angle assumption. So a bunch of simplifying assumptions we discussed before. And then model predictive control is another control approach that's based on looking ahead a time horizon. So you may have a prediction horizon M and a control horizon P. And then for within the prediction horizon, you can compute a sequence of control inputs and then take the first control command at time step k at the current time step, and then move forward one step. Okay. So here's the picture. You are looking ahead at prediction horizon, and then computing a set of control inputs for control horizon, and then taking the first control input UK, and then you move to time step k plus 1, but you throw away the rest of the control inputs you computed. You only take the first control inputs. So control input UK, so all the others are thrown away. And then at the next time step k plus 1, you again compute a set of sequence of control inputs and take the first control input action and throw away the rest. and then move forward. So that's a moving horizon control. So in reality, oftentimes you take the control horizon and prediction horizon to be the same. Oftentimes they're the same. So we denote it as the lookout horizon T. So here's an example where the reference trajectory given to you from the planner. So here it's actually a reference path. So a reference trajectory is path plus speed profile on the path. But suppose right now that we don't have a speed profile, we only need to track the path. So, and then suppose the vehicle has a slightly northeast direction initial speed. So you cannot track the blue trajectory exactly. So you need to, there's some deviations. So you compute a set of control inputs with the resulting hypothetical trajectory given the control inputs and your model, like this, the red trajectory. And then you will take the first control action, control input U at first time step, and then throw away the rest of the control inputs, and then move forward one step and recompute another sequence of control inputs and repeat the process. So is this process clear? So here's the MPC in action, where you are computing a sequence of control inputs at every control time step. So as you can see, the MPC control can be time consuming. So at every time step, you're solving a optimization problem of minimizing a cost function given a set of constraints. If it's a linear MPC, it's very efficient. If it's non-linear MPC, then it's more computationally expensive. So pro is to you can handle constraints explicitly and applicable to linear and non-linear systems. Cons are that computation is expensive. So people have said that PID control is like driving looking at your rearview mirror, because PID cannot look ahead, cannot perform prediction, whereas MPC is like driving looking through your front windshield, because you can look ahead, but depending on the given system model, which must be accurate. If your model is not accurate, so the model is, this is the linear system model. This is a nonlinear system model. The model describes how the state evolves based on current state and control input. So it can be very hard to obtain for complex systems, like a very complex vehicle with a road interaction, which is complex. The road may have snow, ice on it, so the tire friction may be different. So the system model may not be very accurate. So that's the key challenge for MPC, is that you need to have a model that's accurate enough so that the prediction is accurate enough. At the same time, it must be computationally efficient. Yeah, I think I need to another con is to so here's one example of vehicle lateral control. So the model-predictive controller is the high-level controller that takes as input the reference trajectory and produces outputs as longitudinal and lateral forces. The low-level controller I did not discuss. So in the automotive industry, they often use a map to generate control inputs to the car. So essentially, because the control law is expressed as a lookup table, a map, given as input the required forces, and then you do a lookup to get the resulting actuation commands. So that's a nonlinear controller, and the map is tuned with a so-called calibration process. A lot of trial and error, so not a whole lot of control theory. So that's the low-level controller. So for MPC control, we see this control performance measurement. So this example is taken from this Coursera course on Introduction to Self-Driving Cars. And also some of my slides from planning lecture is also based on this course. So these curves show that it seems to be a passing action. So it turns left to pass the front vehicle and then comes back to your ego lane. So for MPC, horizon is a finite time window, and prediction horizon is shifted at every time step. And at every time step, you need to perform a full optimization over the time horizon and take the first control action. So I wanted to explain the kinematic and dynamic model, the differences among them. So the kinematic model uses position, velocity, acceleration, and or further derivatives. They're called the jerk and the snap and other words, which may be useful for improving rider comfort. So we know from the definitions, x dot positions derivative is velocity. Velocity derivative is acceleration. So we'll discuss the kinematic bicycle model later. So it disregards mass and inertia. The dynamic model is essentially Newton's law. Mass times acceleration is force plus a possible friction term, which is proportional to velocity. So think of a block sliding on the floor. You have a force dragging it, and also you have friction with the floor. So for the dynamic model, the control inputs are force and torque. Torque is essentially a force applied to rotate a joint. So it takes mass and inertia into consideration. For example, vehicle dynamics model, both longitudinal and lateral, is a dynamic model. So for example, consider a light vehicle or a heavy vehicle turning a tight corner. So if they have the same shape, then they have the same kinematic model, but different dynamic model due to different mass. So suppose that you perform controller design based on the kinematic model, and you find out, okay, I can control the vehicle based on control input A, the acceleration. If both are controllable kinematically, the light vehicle may be controllable dynamically by control input F, the force. But the heavy vehicle may not be controllable dynamically by control input F due to large mass F may exceed the maximum actuator limit. So it really fits your intuition. So for turning a tight corner, a light vehicle may be able to do it, but the heavy vehicle may lose control. So that's the difference between kinematic model and dynamic model. So this issue is orthogonal from control algorithm. So PID or MPC can be either kinematic or dynamic. So here's the two examples we saw before. The first one, the lateral control of a bicycle model. This is a kinematic model because there's no mass in here. There's no force. Only derivatives of the heading angle theta and velocity as derivative of position. So in fact, this is an even simplified kinematic model because you're controlling the heading angle directly. But in reality, you need to control the steering angle. And then there's this relationship to derive the heading rate from the steering angle, which we'll discuss later. So this example is a dynamic model with MPC, with a high-level controller, MPC, producing forces, which is applied to the vehicle. So these two examples just happen to be PID kinematic control and MPC dynamic control, but you can also have PID dynamic control and MPC kinematic control. You can do combinations. So here's the lab one. Lab one is to perform lateral control of a car to run along a racetrack with fixed speed. So here's the racetrack, and then you will compute the cross-track error based on the distance from the track. And then this is the error term used in PID control. So the problem specification is clockwise traversal. So you are going in a clockwise direction. So for this clockwise traversal, CTE is higher than the is positive if car is outside of the track region, negative if inside. So here's the kinematic bicycle model. Assuming front wheel steering. So and then the rear wheel is the reference point. It's possible to use the front wheel or the center of gravity as the reference point to get different equations. But for this setup, we consider the rear wheel as the reference point. And then state vector is x, y, theta. X is the position of the rear wheel. Yeah, I think it's better to mark it here. Position of the rear wheel and heading angle theta. So control inputs are the delta, steering angle, and vehicle speed v. V is along the vehicle's body direction in this direction, and heading angle theta. So typically angles steering angle delta and heading angle theta are based on clockwise convention with regard to a reference direction. For example, the steering angle, the wheel direction is with regard to reference direction of the velocity v. So that's the vehicle's body direction. So that's delta, the angle between the steering wheel direction and the vehicle velocity. The theta is with regard to reference direction east for this example, which is horizontal. And then any rotation angle, the rate is higher than 0 for clockwise rotation. And then these are the control inputs. Control inputs are delta, where you can turn the steering wheel, and velocity, where you can accelerate or decelerate. So there's a relationship between delta and vehicle length, the distance between the front and rear wheels, and the instantaneous center of rotation, the radius for the instantaneous center of rotation. So the reason that this relationship holds is that if you look at the diagram here, the rear wheel's direction is perpendicular to the line from the ICR to the rear wheel. And the front wheel's direction is perpendicular to the line from ICR to the front wheel. Therefore, this angle here is delta, because both of the lines are perpendicular to the other two lines that define delta. So once you have this relation, you can derive that tangent delta is L divided by R based on this triangle relationship. And then once you have the angle delta, you can derive the rotation rate theta. Theta dot is often written as omega, the angular velocity. Yeah, rotation rate should be really angular velocity. So it is speed times the rotation radius. So the vehicle has a speed in this direction, and then it's performing a rotational motion. So the rotational radius is r. Therefore, the angular velocity is the vehicle velocity times the rotation rate divided by rotation radius r. So that's pretty much the definition of angular velocity. So how fast you're traveling and how large the circle you're traveling on is. And then you plug in the relationship here because this r is a derived quantity. So and it's changing all the time as you're turning in different directions. So and then you plug in r from this relation, you get this relation. So this relates the angular velocity to the vehicle speed v, steering angle delta, and vehicle length l.
I'm sorry, shouldn't it be kind of factor 2 pi or something?
Oh, the 2 pi is already factored in because the theta is expressed in radians, not in degrees. In the Python code, there's a factor of 2 pi. But yeah, if you express the angles in degrees, then you need to have a factor 2 pi.
Well, in degrees would be 360, or the velocity is meter per second, and this is meter, this is per second, and there's number of rotations per second. And that
Velocity.
one rotation should be 2 pi or something. Yep. Okay, don't care. So, or is the velocity measured in something other than meter per second?
Velocity is meter per second.
And this is meter.
Length is meter.
So this is per second.
Yes. Or you can say radian per second.
Isn't it turns per second? Maybe it's radians. Okay, sorry.
Radian per
maybe
second.
Misunderstood something. Yeah.
Not turns per second.
Okay.
Yeah. So if you write out the state equation in matrix form, in the vector form, you have this equation. X dot is v times cosine theta, which is, so the x velocity in the x direction is the v times cosine theta, the projection of velocity to the east direction. And in the y direction, in the north direction, you have v times sine theta. And then you have this relation theta dot equals v times tiny c delta or divided by L. And then the system control inputs are v and delta. And then you have this nonlinear system model. So and given the system model, how do you get the updated equation? So these are the updated equations. So first, let's look at the straight line motion, which is a straightforward translation of the system equation by propagating one time step dt forward. So this is straightforward moving forward one time step dt. But this only holds for small theta dot times dt. So it's described as straight line motion, but it's approximate because the real motion is rotation along a instantaneous center rotation ICR with a radius r. So for the accurate description of the circular motion around ICR, you have this this equation where the r is derived from the previous relationship here. So in the Python code, the derivation is quite clear. So let's go through the Udacity's Python code for computing the vehicle motion. So these steps are to apply noise. These are useful for state estimation, which we did not discuss in this course. That is common filters and particle filters. So these are not relevant to us. So we set them to all to 0. And then we execute a motion if the so the turn is the turning vehicle turning angle, the change in theta in the time step dt. So that's theta dot times dt. And then if the change in vehicle heading is small, if absolute value of the turn is less than the tolerance, you can approximate this motion with a straight line motion with the equation we saw before, the approximate equation. So here you see in the code, they have this pi, 2 pi. Oh yeah, so they have this modular 2 pi. Actually, yeah, because if it's higher than 2 pi, you just subtract 2 pi. This doesn't change the any operation. So then for the circular motion, the way the computation is done is to first you derive from the rear wheel position xy, you derive the coordinate of the ICR, instantaneous center of rotation CX and CY, based on this formula here. The reason, again, look at the angles. This particular angle here is theta because of the perpendicular relationship. So this line here is perpendicular to the east line, east horizontal line. And this line here is perpendicular to the vehicle length. Therefore, this angle here is theta. So the coordinate of the ICR, the x-coordinate is the vehicle to rear wheel position x-coordinate minus a r radius times sine theta. So this term here, based on the triangle here, and y position of the ICR is the vehicle rear wheel y position plus r cosine theta. That's the length here. So once you derive the ICR's coordinates, you can perform a rotational motion around this ICR for a angle of turn theta dot dt. So you add the theta dot dt to the current vehicle heading to get the new heading. That's the orientation or heading of the vehicle. And then based on the new heading, after adding the turning angle, you get a new coordinate after rotation, which is from these ICR's coordinates, you perform reverse derivation to get the xy coordinate of the rear wheel. So perhaps there's a small rotational motion, and then the new position is perhaps in here. And this angle here is theta dot dt. So that's how you get the updated equation here. So you first perform a subtraction to get the coordinate of the ICR, and then you perform a small rotation with a small angle here. It doesn't have to be small, it can be large because this equation is accurate. And then you perform a reverse transformation to get the xy coordinates. So is this derivation clear?
Yes.
Okay, very good. So I'm just looking at the derivation to see if I missed a 2 pi somewhere. The modular 2 pi, do I need that? Well, I think you don't need it because you're performing the theta with cosine and sine functions. So even if you have the extra 2 pi in there, it wouldn't change the result. Yeah. So in the Python code, they have this modular 2 pi, but if you remove it, I think it's fine.
It's just if you turn several rounds, so you don't end up in like 100 pi or some strange angle.
Yeah, but even if you have 3 pi, that's fine because at the end you're taking cosine and sine functions.
Yeah, so it shouldn't matter.
So here's a little bit derivation, not that important, to show that the straight line motion with a steering angle delta is 0 is a special case of circular motion. so equivalent to a circular motion with radius infinity. So first, let's look at delta goes to 0, then the rotational radius goes to infinity, and theta dot, the angular velocity goes to 0. So which is intuitive because small steering angle delta leads to slow turning rate, slow angular velocity. That's the better term. Oh, okay, yeah, theta dot. And then we get a special case for the straight line motion to improve computational efficiency for small delta and theta dot, and also to avoid division by 0. However, you can derive the special case from the accurate general case. So here's the accurate equation here, and then you realize that this term here is actually the derivative sine function times the theta dot dt. So that's pretty much definition of a derivative, assuming that a straight line connecting the starting point and end point, and then the derivative is the slope of the line. And then you plug in this term into the equation, and you cancel out the theta dot term and get the this term, which is the term for the straight line motion approximation. Similarly, for the y term, you get the y motion as a special case of the circular motion. And you can check the validity of these equations. So if theta is 0, theta 0 means that the vehicle is the heading is horizontal or east-west. That's the vehicle heading with theta 0. And then you're traveling east. So the x is updated at every time step, and y stays constant. Sorry, missed the dt here. And then if theta is 2 pi, it's pi, and then you are moving west. If theta is pi over 2, you're moving north. So by plugging in the equations. So in the Python code, the run function performs a PID control operation to define the steering angle direction delta, and then you do a move operation, which is the bunch of messy equations we saw just now. So to get a trajectory that is the actual trajectory traveled by the robot. So notice that the control law here, we have a minus sign at every term. So it's designed for the clockwise travel direction. With this particular definition of control law, you get the effect that if CTE is positive, which means that the car is outside of the track region, the control law will cause the steering angle delta to decrease. The car turns right, and vice versa. So if you look at the track, so if you're somewhere in here, the vehicle is turning in a clockwise direction, and then if it's here, then it should move. It should turn in this direction to go back to the track. If it's here, then it should turn in this direction. In both cases, if you're outside the track, then you should decrease the turning steering wheel angle. And then what does it mean to decrease the steering wheel angle? Remember that the angles are defined based on counterclockwise convention. So by decreasing it, we're turning right. So, and then if you're inside the track, we need to increase the turning steering wheel direction, which means that we're turning left. So we are inside the track and we're in this direction, and we need to turn left to go back to the track. So all of these definitions are coupled. So it relies on the assumption, first, that you're traversing the track in a clockwise direction. Second, your convention is that the angles are based on a counterclockwise convention. And then your control law looks like this. If you change any of the factors, if you travel in a counterclockwise direction along the track, or if your convention for calculating the angles is clockwise convention, then the equation wouldn't be right. You're missing a minus sign.
I have a little question. So this is on the global coordinate system, XY. So I think in a vehicle, you have just some kind of local, the street turns right or left or something.
So the vehicle state, x, y, and theta state vector is in a global coordinate. So somewhere you have global 0.
Some GPS positioning or something. Yeah.
Yeah. So somewhere you have a global point of 0, and somewhere you have a global direction of 0. For example, east. So no, it doesn't matter how you define the global coordinate. The point is that they're global. They're in reference to a global reference frame. And then the steering angle delta is in reference to the vehicle's heading direction. So delta is kind of in a local frame.
Yeah, and the error is if you're kind of to the left of the road or to the right of the road. This on the next slide.
The
CTE is
the CTE,
like if it's larger than 0, you're to the left of the road. And if it's less than 0, then it's
not to the left, but to the outside of the track. So it's here and it's here. A CTE is all positive. If it's inside, it's negative.
Yeah, but on a random kind of track, it means you are to the right of the desired position. So you should turn left.
Yes.
And vice versa. So it's not connected to this particular racetrack.
With the assumption that you're traversing in a clockwise direction. If that assumption is reversed, then you need to reverse the sign.
Okay.
Right?
So,
because
but then the speeds are negative or okay, don't. But if you look in a local frame, so if you got the error positive, okay. In a real situation, you have the sensors and all this stuff with local facts.
well,
data.
Yeah. So in a real car, the delta is measured by a local sensor relative to the local frame. But theta and xy are global coordinates.
Yeah. So if you're in to the left of the road, it's natural to turn right, so to say, locally.
That's only when you are traversing in the clockwise direction. Suppose you reverse it. Suppose you traverse in the counterclockwise direction. Suppose you want to drive in this direction. And
Yeah.
then if you're on the left of the road, you want to turn left to come back to the track, right?
No, in that case, you are on the right of the road, to the
Oh, in
right
the
of the
right.
road. Yeah.
And then you try to
Turn left.
turn left. Oh, yes, that's right. Yes. Okay. So in any case, I hope this bicycle model is clear. And the twiddle, let me explain this in detail. Let me finish this before we take a break. That's where I cut the video because I want the videos to be in segments, where each chapter is a segment, which is easier for you to look up. So the twiddle function, just the three PID parameters in turn. The P is in here. It has three control parameters, initialized all to 0. So length P is 3. You have PID 3 parameters, and then you update the P with dP, kind of like a gradient descent operation. Increment PI with amount dPi, and you run the robot for two n time steps in this program. You compute the error. If the error compared to the previously best error, if it decreases, then it means that our adjustment of PI is in the right direction. So this is the right move. We're moving in the good region of the parameter. And then we save the current error as the best error, and then increment the step size. So we're moving in the right direction. We go in a bigger step, not time step. Otherwise, if the error has increased after you made the adjustment, it means that you adjusted in the wrong direction. You shouldn't have done that. And then you reverse and adjust in the opposite direction by adding -2 dP. So you're stepping in the opposite direction, starting from your initial position with the step size dP. So by doing this, and then yes.
Can I have a little bit comment on this as well? Sorry, and that is if you work with control, if you start with a p-value, the proportional part, and it works okay. But then when you add an integral part, you have to reduce the proportional part to keep stability in a control system. You know, you can't select the best p with the integral part to 0, because then when you increase the integral part, you have to reduce the proportional part. So this, for me, seems a little bit strange that you first set the P and then the I and then the D, because then afterwards, if you add the differential part, then you can increase the proportional part. so they are kind of connected, those parameters. But maybe I misunderstood this twiddle algorithm. But for me, it looks like it sets the first one first, and then the second one, and then the third one.
No, you didn't misunderstand it because the author, Sebastian Thrun, who is the voice in the videos I showed before, he was the first he was a Stanford professor. He worked in the DARPA Grand Challenges and then got a position in Google to direct the self-driving car project. And then he quit Google and started Udacity as his startup. So Sebastian Thrun is a roboticist. He's not a control theorist. Maybe if Sebastian talked to Carla, he could have realized that this issue.
Actually, I talked with him like 25 years ago in Switzerland. And we were talking about reinforcement learning at that time. So we'll mention that a little bit more later on. But he's a very good guy. But as I mentioned, we should have Leonid here. Maybe he could also comment on this. But this is a good, it might work okay. But from a strict control point of view, you should kind of adjust them all at the same time in some way.
Yeah, so twiddle is strictly a heuristic. So obviously you can add additional rows to the heuristic. For example, the row of decreasing P parameter when you increase I parameter. So all of these can be added. So this is just a very simple heuristic.
Yeah, sure. Good enough, I think.
Yeah. So let's continue. Now, at this point, we realize that we adjusted in the wrong direction. We have reversed directions. Now what? Okay, now we run again. Run robot again and get a error term. If the error decreases, it means that the reversed direction is okay. We are in the right direction. So we keep the error as best error and again increment the step size. Otherwise, we are in the wrong direction. Now what do we do? So we could just reverse directions, but then you may be reversing and doing oscillation, never making any progress. So if you're always reversing, then the P pretty much stays around the same place. To avoid oscillation, we don't reverse the direction. Instead, we adjust the step size. We reduce the step size. So that's the reason why we're not reversing direction here.
And I noticed, sorry for my comment again. So we have this for loop where you adjust those, but then there's the outer while loop. So you redo the P adjustments after you have selected a integral part. So it should work okay. So now there is an inner loop for E in range, and there is an outer loop while some dp is greater. And when it runs the next while, it redo this
yes
adjustment of the P again.
Yes. So you're doing adjusting P, adjusting I, adjusting I'm sorry, P and then D and then I, because the parameters are proportional, derivative, integral in that order. So and then you are repeating the process until you get a some dp does not exceed a tolerance, which means that your step size is so small that you're not adjusting anymore. Then you stop. Okay, any questions on this twiddle function? So twiddle versus pole placement. So twiddle is like a gradient descent approach to tuning PID controller. Notice that the controller design is based on the accurate bicycle model, which is highly nonlinear. So this is the bicycle model with the sine, cosine, tanity in there. So it's nonlinear. So even though it's nonlinear, PID can still be applied, except that you cannot use the pole placement, the control theory to design a PID. You must tune it with a heuristic rule because of the nonlinearity in the system model. Therefore, with this twiddle, it's universally applicable to any system by gradually adjusting the parameter with adaptive step size dp until convergence to a minimum best error given the DT's DP's upper bound. So when DP's when the parameter P's step size adjustment size DP stops changing, you stop. So it's a very generic approach to tuning controllers, whereas previously we saw the pole placement approach for PID control design, where we did approximation, where sine theta is approximated as theta with a small angle assumption. An additional simplification is to assume that the angular velocity theta dot can be directly controlled. So theta dot as u, the control input, instead of delta. So we are completely ignoring the bicycle model's steering angle variable. We are assuming that somehow we have a magical vehicle where we can directly control the heading, which is not realistic for bicycle model, obviously, but it's a simplification. So so in the course video, there is an error. So if you watch the video at this link, he said that if you set these two parameters, say KD KI equals 0, this goes into a P controller. But it's not true because they're initialized to 0 here, and then afterwards in twiddle, they're adjusted. So they may be incremented or decremented to be non-zero. So it's still a PID controller.
But aren't they scaled with a number? So 0 times 0.9 should still be 0.
Oh, D param. Oh, I think I made a mistake. Oh, yes. It's not an error. Sorry. I saw this as yeah, it's not an error. That's the DP. I thought it's P.
Yeah. Okay.
Yeah. So the proportional parameter is changed.
So the only thing is maybe it wastes a lot of time trying to modify those. But yeah.
Okay, that's good.
Oh yeah, you have this in the next, yeah. Change the for loop.
So to turn it into a PI or PD controller, you need to change the for loop to only adjust change the for loop.
Actually, you don't need to do that, but to save some time, it could be good to change it. Unless it will search for PI and PD controller parameters without changing them, so it's a waste of time. But it still works.
No, if you look at my lab assignment, my lab 2 here, let me go through it. So you start from your Python program from lab 1. First, change the track shape to a round circle with radius 50. So you need to modify the function CTE. The reason I did this is because I wanted you to know how to set the CTE function. Actually, it's not important. You could have used the original track shape. So and then modify the twiddle to tune a P controller holding the KI KD to 0 and PI controller holding KD to 0. PD controller holding KI to 0, and then a full PID controller. So initialize the parameters all to 0, and then you can adjust the twiddle function to realize these different controllers. So the part 2 is to set a very high vehicle speed. So the original vehicle speed is 1 in the Python program. And then if you set it to 10, you may lose control, no matter how hard you tune. So after the twiddle procedure finishes, you get the setup parameters, PID control parameters, but the control performance may be very bad. And then to keep control, you can either increase the track length by increasing circle radius. Obviously, you run a larger track, that's fine. Or you can reduce the time step size, dt. That's the sampling rate for the controller, with a proportional increase of n, where n, 2n is the simulation time steps in run function. If you do these two changes simultaneously, you can keep the local simulation time constant. So let's take the latter approach and tune a PID controller with twiddle for speed equals 10. Try different time step sizes, dt, until you get a low tracking error. So if you look at the PowerPoint in this description of the bicycle model, I said the Python code assumes controller time step dt equals 1. So I have dt in my formulas, but it's not, dt is not in the code. So you just need to add in this dt factor in the Python code. That's all. And then a quick shortcut is to increase the PID controller gains based on existing solution for original speed of 1 and simultaneously reduce dt, both proportional to speed increase. So yeah, you have the original solution for speed 1, then you simply multiply the gains by 10 and decrease the time step by 10. And you get the same controller and same effect on the system. But in reality, you will not have an existing solution to fall back on, and you must tune the PID gains from scratch. So that's why I give this assignment to ask you to start from initial gains of 0, and then use twiddle to tune the controller to the best performance. So the tasks are, first is for a speed of 1, you tune 4 controllers, P, PI, PD, PID, and plot the results. And for task 2, you can see that it's unstable for time step 1, the default time step, and then you adjust your dt and until you achieve a low tracking error. So any questions on the assignment?
I had a little question about you control 2 things, like the deviation and the orientation of the vehicle. So sometimes you need to weight them differently, I think. Which is most important, to stay close to the road or to orientate the vehicle in the same?
Oh yeah, so the program is trying to minimize the average error. That is, if you look in the program, so let me look for that track. Here's the track. So the error is the final error is computed by adding up the per step error. So that is you have the actual trajectory is a set of sequence of points because of the finite time step. So it maybe looks like this. So that's the actual trajectory. And then you compute the average of the cross-track error based on this obtained actual trajectory. So this error is affected. So it is the distance to the center of the lane. But to reduce the error, you need to adjust the vehicle heading in the process, and it's a nonlinear equation. I mean, it is color set something that's reasonable. If you have two objectives, you should put a weight on each objective. But in this case, the aggregate, the total error is actually a function of both factors. One is the heading, one is the distance to center of the lane. Are you happy, Carla?
Yes, yes, they are connected, of course, but you can have a slalom driver who still are on the track. When it oscillates around the track, it could be better than just try to follow the track. If you are driving in the forest, for instance, with a slippery car, you never follow the track with the car's orientation. It's always a little bit off.
Yes, I just thought of something. So you may introduce another error definition, which is the aggregate heading error relative to a heading of 0 as theta. So and then it figures in the factor. First is the distance to the track. Second is the heading. Always left and right oscillating, or is it going straight most of the time, right? So that's two factors.
Yeah.
Yeah. But in this definition of error, we are just counting the distance to the center of the track, to the center of the lane, which is affected by heading and the distance. Okay. I think we can take a break and come back. Let me stop the video so we have a separate video for the next chapter.